Let's look at the factorials and Fibonacci numbers. So what is factorial? So n factorial, this is n factorial, is defined as 1 into 2 into 3 till n. So by the definition, we can say recursively n factorial is going to be n into n minus 1 factorial. This is how we denote the factorial, this exclamation sign, right? 0 factorial is going to be 1. That's the base condition for this recursion, right? Now let's look at the Fibonacci numbers. Fibonacci number f of n has a formula f of n minus 1 plus f of n minus 2. This recursion you can see. The base condition is f of 0 is going to be 0, f of 1 is going to be 1. So let's say they ask you what is 3 factorial. So it's very simple. 3 into 2 into 1. Simple. It will be 6, right? Let's say they ask you second Fibonacci number. So f of 0 is going to be 0 and f of 1 is going to be 1. So f of 2 is going to be f of 1 plus f of 0, which is going to be 1 plus 0. It will be 1. So f of 2 will be 1. I hope Fibonacci number and factorial are clear to you. One more thing that I need to highlight is that to compute f of n, you need to go to n minus 1. Then you need to go to n minus 2. Then you need to go to n minus 3. Right? Till you reach the value 1. So, the normal case to compute f of n, you have O of n time complexity. This is the normal case. There is another method using matrices to compute f of n efficiently. We can deep dive that later on, but I just want to highlight it here as well. So if you observe carefully, you have f of n as f of n minus 1 plus f of n minus 2 for Fibonacci numbers, right? If you observe carefully, you have coefficient 1 here and you have coefficient 1 here. I am going to take those coefficients with me. So f of n is dependent on f of n minus 1 and f of n minus 2. So I am going to write those two here. F of n minus 1, f of n minus 2. And what I want to compute, f of n. I will write those coefficient here as well. 1, 1. In matrix multiplication, you know that you are going to multiply this with this. So you get the f of n, no problem. But you have f of n minus 2 here for n minus 1. So for f of n, you will definitely need f of n minus 1. So we will write here 1 and 0. And there is a multiplication. If you know the matrix multiplication, you can directly see we can compute f of n by multiplying this matrix with this. Very, very simple, right? So we saw that we can represent f of n and f of n minus 1 as 1, 1, 1, 0 into f of n minus 1, n minus 2. The base condition we do know, that is f of 1 is going to be 1 and f of 0 is going to be 0. So if I write something like this, you will get f of 2 and f of 1. Correct? Let's say they want to compute f of 3 and f of 2. How it will look like? Well, it's going to be 1, 1, 1, 0 multiplied by f of 2 and f of 1. Correct? But now this f of 2 and f of 1 can be replaced with this. So it will be something like 1, 1, 1, 0. Then again you will have 1, 1, 1, 0. And here you will write f of 1, f of 0. Right? See, this will be this. And this we have replaced with this value, right? Right here. I hope this makes sense. So f of 3 and f of 2 is going to be this matrix multiplied by this matrix into our base condition. By that extension, you can say f of n minus 1 is going to be 1, 1, 1, 0 to the power n minus 1 into f of 1 and f of 0. Now this is just a matrix multiplication, remember, and you have n minus 1 power, so you need to multiply this matrix with itself for n minus 1 times. And you know already how to compute this particular value in log n time using binary exponentiation. You just need to write a code for matrix multiplication. Matrix is a 2 by 2 only, so it will be very simple to write a code. You just need to write a code for matrix multiplication, and then you will write binary exponentiation code to compute this quickly. Thus you know f of n in just log n time. So let's say f of n has a dependency on n minus 1, n minus 2 and n minus 3. Coefficients are x, y and z. Then you can represent this particular expression by using matrix multiplication. How? So let me write that. First you write coefficient x, y and z. Okay, good. Then you write all the values on which f of n is dependent. F of n minus 1, f of n minus 2 and f of n minus 3. Right? Then you write the result set. It's going to be f of n. See, for n minus 1 you have n minus 2. So for n you will get n minus 1. For n minus 1 you also have n minus 3. So for n you will have n minus 2. Okay, now you decide all the other values in this matrix as well, this particular matrix. So let's decide those. To get n minus 1, you will write 1, 0, 0. To get n minus 2, you write 0, 1, 0. Now this is very easy to compute. You can compute f of n in log n time by just writing here n minus 3. So you can convert any recursive equation where f of n is dependent on its previous values into a matrix multiplication operation. And you can compute it fastly by using binary exponentiation. So this is very important technique. We will look at this technique later on as well. So let's go to the next topic, which is logarithms. Logarithm of a number x is denoted as log x, where k is the base. So the useful property of this logarithm is that it will tell you the number of times that we need to divide x by k before it reaches 1. What do I mean by that? See, you have 32 here and base is 2. So the value of this is 5. That means you need to divide 32 by 2 5 times till it reaches 1. Here 32 you get 16. Here we are dividing by 2, okay? From 16 you get 8. From 8 you get 4. Again 4 divided by 2 you get 2. Then 2 divided by 2 you get 1. So it will tell you the number of times that you need to divide 32 by 2 to get 1. There is another formal definition for logarithms, but this is the most important property that we are going to use heavily going forward. That's why I am highlighting that here. There are some properties of log. Log a into b is just the addition of log a plus log b. Log x to the power k is just k into the log x. Log a by b is just log a minus log b, and you can take out this base and write it under division with some common k as a base. So these are the 4 most important properties of log. Okay, so next is prime factorization. So prime factorization is very simple and we have already gone through, we have already seen it in C of Eratosthenes. But there is something called smallest prime factor that we are going to introduce here. So smallest prime factor, as the name suggests, is the smallest number which is prime and which can divide n, right? So smallest prime factor of 60 is going to be 2. Smallest prime factor of 30 is going to be 2. Same thing, smallest prime factor of 5 is going to be 5. So how exactly are we going to compute the smallest prime factor? We have already gone through the code in C of Eratosthenes. I am just going to highlight it here. It's very simple and straightforward. First, smallest prime factor we initialize as themselves. Smallest prime factor of I is going to be I. That's how we are going to initialize at first. We will start from I is equal to 2. We will go till root of max n, right? So I into I is less than or equal to max n, and we are just going to iterate. Again, we have already gone through this condition. Why do we need I into I? I will just highlight it here as well. Let's say A into B is n. Then it is impossible to have A greater than root n and B greater than root n. It's impossible, because if you multiply them together, then you will have A into B, which will be definitely greater than root n into root n, which tells you that A into B is greater than n. But remember, A into B is just n. So you can never have two numbers or two prime factors where both of them are greater than root n. At most you can have only one prime factor which is greater than root n, not both of them. So we are just going till I into I. If you have gone through the C of Eratosthenes, then you understand what this if condition is, and you understand the importance of starting point of J as well. We have taken the examples there for your better understanding. Please go through that video if you haven't gone through it. So we first check if smallest prime factor of I is I. If smallest prime factor of I is just I, then that means that value I is a prime number. Then for all the multiple of that prime number, we are updating the smallest value, right? So if smallest prime factor of J is J and J is multiple of I, then we need to update the smallest prime factor of J as I. Makes sense, right? If smallest prime factor of J is J, that means no other number has divided it yet, but I can divide it. That's what this loop is, right? So we are going to update the smallest prime factor. See, if you don't understand this code or the time complexity of this, the time complexity of this is n log of log n. If you don't understand this code or the time complexity, I highly recommend you to C of Eratosthenes video. Now if they ask you to give me the prime factors of n, then it's very simple. By using smallest prime factor, you can get all the factors of n. See, as I mentioned, the time complexity of smallest prime factor computation is n into log of log n, and factorization will take log n. Why? Remember, smallest prime factor of any number can be 2, and if you look at the code, we are always dividing it. So the value will be reduced by 2 at every single stage. N by 4, then you will go to n by 8, then you go to n by 16, right? And we have already seen log x base k represents number of times x needs to be divided by k so that it will reach 1. This value will be represented by log x base k, right? So you can say that this loop will run till the value of n reaches to 1. And we are dividing at least by 2, so you can have these many steps only. That's why the time complexity is log n. If you don't understand this particular smallest prime factor, please go through the C of Eratosthenes. It is very important. You will understand the importance of this if condition. You will understand how to decide the starting point of J. You will understand this I into I as well. Okay, so next is combinatorics. NCR. So what is NCR? Well, it is number of ways to choose R elements from n elements where order does not matter, right? This is basic algebra, so I am not going to deep dive, but the formula is n factorial divided by r factorial into n minus r factorial. It's very simple. So 10c5, so it will be 10 factorial divided by 5 factorial into 5 factorial. So because this factorial grows very big very quickly, they usually ask us to compute NCR modulo m, where m is usually a prime number, that is 10 to the power 9 plus 7. We have already seen it in modular arithmetic. Okay, So this NCR can be written as n factorial into r minus 1 factorial mod inverse and mod inverse of n minus r factorial. So we can pre-compute these values. Why do we need to pre-compute? Well, usually they will never ask you to compute NCR directly. It will be a part of some kind of question where you need to compute NCR for various n and r combination. So it will always be better to compute the factorial values rather than computing for every single query. It will always be better to pre-compute the factorial value as well as the inverse factorial value. So it's very simple. So factorial of 0 is 1. As we have seen the recursive approach already, factorial of I is going to be factorial of I minus 1 into I mod m. Now how exactly are we going to compute the inverse factorial? Well, you know from the Euler-Stoughton function video and modular multiplicative inverse video that a to the power phi of m is equivalent to 1 mod m. That means a to the power phi of m minus 1 is going to be the modular inverse of a. This phi of m is going to be m minus 1 because m is usually a prime number. So this inverse factorial of n can be computed using binary exponentiation algorithm where this value of a is going to be factorial of n. Remember, this phi of m is m minus 1. So you will have m minus 2 as the power and you will get the inverse factorial of n. Now, here is the trick. Once you know the inverse factorial of n, you can compute directly all the factorials. How? So this is what we are going to do for computing all the inverse factorial of I. Let me prove this to you. So this is what we want to prove. See, inverse factorial of I we can write is I factorial to the power minus 1 mod m. So we can write I plus 1 factorial as I plus 1 into I factorial. Take the inverse. I plus 1 factorial inverse is same as I plus 1 inverse into I factorial inverse. Just move this I plus 1 inverse here and you will have I factorial inverse, which is this, with I plus 1 factorial inverse, which is this, and you remember you have moved this here, so this I plus 1 factorial will be multiplied here directly. You can take mod on the left and right side and you will have this particular formula. This is inverse of factorial I, this is inverse of factorial I plus 1, and this is I plus 1 directly. And that's what we have written here. Once you compute the inverse factorial of n, you don't have to compute inverse factorial for every single I by using binary exponentiation. You can directly utilize this particular observation to compute the inverse factorial of I. So factorial is computed in O of n time. Inverse factorial for all the I is also computed in O of n time. So now NCR will look something like this. Factorial of n, inverse factorial of r into inverse factorial of n minus r. So when they ask you a question where you need to compute NCR for various combination of n and r, you just use this pre-computation. You compute the value of all the factorials, you compute the value of all inverse factorials and you use directly those to compute NCR. Very simple, right? Please go through this video once or twice, and if you don't understand anything, just comment down below.